Hi guys, and welcome to this video on we're going to have a look at exploring how to differentiate or derive power functions and polynomials. So let me just change that pen to something a little thicker. So we're having a look at the differentiation of power functions plus polynomials. Okay, so basically what that means when we're looking at polynomials is anything that sort of fits this pattern where we have a coefficient and a power of x. So for example, let's say we had 7x squared and we're wanting to derive that. Now a polynomial has usually more terms than that, but what we're going to have a look at for the start is just deriving polynomials that have just one or maybe two terms. And what we're trying to look for is some sort of way in which we can shorten this rather long method of deriving. Now you might recall from first principles we have to basically figure out this limit, and that is a rather long process. So what we're after is looking, hey, for this kind of function, is there some sort of shortcut? And the way that we're going to do that is we're going to have a look to see, is there any sort of pattern that occurs when we derive polynomials, and then can we extend that to other power functions. Now what we're not going to do here is to look at a formal proof of this, because to do a formal proof, okay, let me just make a note over here, to do a formal proof we'd have to go into in more detail something called the binomial theorem, and that's going to be rather too time consuming for us at the moment. What I might do is to post a video about the binomial theorem where you can have a look at that if you're interested in, but let's have a look at this pattern approach for now. So let's start off with, in fact, this example here. So here's our function, and let's derive this from first principles. So I'm taking the original function, substituting x plus h into it, subtracting the original function, dividing by h, this first principles approach here, and then we need to calculate that limit. And the way that we've done this in others, expanding out that bracket, let's now expand the 7 into that. And as been the case with all these other polynomial type ones that we've been doing, we end up with some simplification, and we've left with these two terms here, both of which have a common factor of h, and we can take that out the front. Now we can cancel that common factor of h, and now we can substitute safely the 0 into what's remaining, and we end up with 14x. Okay, so all good. Let's put this on a new page then. So here's our function, and here's our derived function. Now I'm going to put down a few other results, and these can all be verified using first principles, but just to save a bit of time I'm just going to put down the raw sort of results. Our d here is some sort of constant, dx to the power of 4, the derived function 4dx cubed. And let's put down a couple more. Let's put 7x to the power of 0. Now that would actually just be 7, and the derived function actually works out to be equal to so that would just be 7, and the derived function turns out to be 0. Now I might just want to come back to that and say, well, why is that the case? Does that fit that pattern? And let's put another one where we've got a couple of terms this time. Let's say we had 5x to the power of 4 minus 7x squared. The derived function would turn out to be 20x cubed minus 14x. Now all of these here can be proven from first principles. Some would take a little bit of work, others would take quite a bit more work to do, but they can all be verified. Now what I'd like you to notice is that we have, even if we've got a couple of terms here, but each of those terms fits that sort of pattern, a number and some sort of power of x then. And the derived function, if you look at that, you might notice that each time if you took the power times the number in front and then subtracted 1 from that power, in other words a times n, and then subtract 1 from the original power, okay, then you end up with the derived function. So let's verify that. 2 times 7, yeah, that's 14. Subtract 1 from that power, you get x to the power of 1, which is what we've got here. 3x cubed, well the coefficient is a 1. 1 times 3 is 3. Take 1 off that power, you get squared. Next one, 4 times d is 4d. Take 1 off that power, you get x cubed. Does this one fit? Well, yeah, it does. Okay, this one, if we just put this down here, that was 7, and x to the power of 0 is 1, so that's still 7. The derived function would go 7 times 0, x to the power of 0 minus 1. Well, anything times 0 is 0, even if the power happens to be -1. So yes, even this result does fit that pattern. And this one here, 4 times 5, 20. Take 1 off that power, you get x cubed. This next term here, 2 times -7, -14. Take 1 off that power, you get x to the power of 1. So yes, this does seem to be holding for any polynomial type situation. Now if I just swap to a new page, this also can apply to other powers of x. So we're going to just extend that to say even if this power of x is not not a whole number, okay, then yes, it still does apply. This rule would apply to others. So for example, let's say you had y equals the square root of x and you're asked to derive it. Well, we can rewrite that as a power of x, x to the power of a half, and then we can derive it. So half times x, because the coefficient's 1 times a half is a half, and we subtract 1 from that power. Well, that can be simplified to half times x to the power of -1/2, which is a perfectly good answer, but can be written in more tidy form. You might recall that x to the power of negative something can be rewritten as 1 over x to the power of that something. And so this could be a half times 1 over x to the power of a half, or 1 over 2 x to the power of a half. or even better, 1 over 2 root x. Okay, because x to the power of a half is that root x, and it's on the bottom there. Okay, which would be the correct answer? Well, that would be correct. That would even be correct. That would be correct, and that would be correct. Which one would be better, and mathematically, from a mathematician's point of view? Well, this one here. In terms of the exam, which one would be marked right? Well, I suspect that any of these three here, probably this one looks a little weird, but is strictly speaking still correct as well. Okay, so let's do perhaps one more example. Just erase this here. So let's take another example. Let's say we had y equals 7x to the power of 9 minus 1 over x to the power of 3. Okay, well, let's rewrite this in a way that we can apply this rule here more easily. X to the power of 1 over x cubed can be written as 1 times x to the power of negative 3, or just x to the power of negative 3. So deriving 9 times 7 is 63, take 1 off that original power. Okay, that's what that first term would be. Negative 3 times negative 1, the coefficient's 1 there, so it'll be positive 3, or strictly speaking negative 1 for the coefficient. And then subtract 1 from the power. Now be careful, it's negative 3 already, minus 1, negative 4. So that would be that. And let's write it in a nice tidy form. 3 would be on top, x to the power of 4 would be on the bottom. Okay, let's, I did say that was the last example. Let's take just one more. What do you do if we have some sort of weird sort of root thing, like let's take 8x squared plus, let's say, the cube root of x to the power of 5. Well, we need to put that root thing squared into a power form. Now remember, that's the cube root, so that's x to the power of a third of x to the power of 5, so that's essentially the same as that. So that would be x to the power of 5 thirds. And now deriving 16x plus 5 thirds x to the power of, well, what would it be? 5 thirds take away 1 is the same as 5 thirds take away 3 thirds. That's going to be 2 thirds. And that's a perfectly correct answer in a more mathematically kind of way of putting it, back in sort of surd or root form. Okay, would have that's 3 on the bottom there, but what would this be? This would be 5 times the cube root of x squared over 3. That 3 is the cube root. Okay, so that's it, guys. That's just demonstrating, basically using some patterns, how we can get this, and then a few examples of using it. Okay, catch you in class tomorrow.